everyone, and welcome to Science the News DayCon 2019. My name is Cari. I'm doing my PhD in theoretical physics at Harvard University. I work in particle physics. And today I'm going to talk to you about something that I spend a lot of my research time thinking about, but also shows up a lot in our daily lives as well. And that is symmetry. Okay, so I want to start out my talk by asking a question that I don't think has an answer to. What makes something beautiful? I'll give you all a second to think about what makes something beautiful. Okay, ultimately I think that this is a very difficult question because it's really hard to define. There we go. What beauty is. Alright, so lots of things have beauty for lots of different reasons. Alright? And when we look at something that's beautiful, it's very clear. It's very easy to recognize beauty, but it's quite hard to define it. So maybe the right question isn't to ask what inherently is beauty, but instead to ask how does beauty make us feel? Maybe that's the right question to ask instead. Okay? So beauty can be a lot of things. Beauty can be striking. It can be something we've never seen before. It can be so awesome and inspiring and bold that it's just beautiful is the only word that we can use to describe it. Beauty can be a functioning clicker. Beauty can be calming, okay? We can think of scenes that we've dreamed of or seen before in very surreal situations, and when we see this again, it can inspire this feeling of beauty when we look at it. Alright, and along that same arc, beauty can be simple. It can be just a bunch of shapes put together, but in such a comprehensive way that we know exactly what we're looking at. There's beauty in this organization and simplicity. Okay? So as a scientist, when things are simple, my life gets a lot better. So I really appreciate the beauty of simplicity. Okay? And so one of Einstein's most famous equations, E equals mc squared, is a great example of how something can be simple and therefore beautiful. There is so much information about my field packed into this very tiny equation. Okay, and to me, a universe that can be described with simple and profound laws of nature is a very beautiful thing. Okay, so I want to, punchline. Okay. I want to distinguish between two related concepts, okay? One is simplicity and one is triviality. So what I'm not saying is that trivial things are beautiful, right? So the easiest shape that we could possibly construct is just having three lines intersecting, all right? And that's our triangle. So this is a pretty trivial shape. You can do some more interesting things with it, but as far as shapes go, this is not winning any awards, right? Okay? But instead we can take this very simple shape and build something much more complex and beautiful out of it. So this is called the Sierpinski's triangle. And it's built on two very simple things. The first simple thing is the triangle itself. Okay? And the next simple thing is a rule. Every time you see a triangle, put another triangle in it and repeat it until infinity. Okay? And so you can generate this really beautiful fractal shape called the Sierpinski triangle just by taking the simplest shape and a very simple rule of what to do with it. Okay? So this has a simple structure to it, but I would not say that this is trivial, right? Whereas our triangle is a pretty trivial thing to draw. Okay? So the fact that we can get these very complicated objects from something that's pretty simple is an example of symmetry. Right? These underlying patterns that show up in these more complex events or more complex structures that are built out of these very simple building blocks, that's an example of symmetry. Alright, so I'm sure a lot of us have heard about symmetry before, and I want to give a definition that I'll use throughout this talk. So a symmetry of an object is an operation that produces a new object that is indistinguishable from the original. Okay, so that's a lot of words. Let's see it in pictures. Let's see the pictures. There we go. Okay, so let's say that we have a square. And this is just a simple square, and I put a blue dot on one of the corners just so we can keep recognizing it, right? And the operation that we're performing on it is a rotation by 90 degrees. So we just take it on one side and move it to the other, right? And this blue dot traces out where that corner will go after each operation. But now I remove the blue dots, and they're indistinguishable. Okay, so this rotation by 90 degrees is a symmetry of the square. symmetries we can talk about. One of the easier ones is a reflection symmetry, in which if we were to put a mirror along these red dotted lines, we would recover the entire shape as before. Okay, so this is one example of symmetry. All right, and it shows up a lot in art. So here's an example by Diego Rivera, where we see the symmetry very present in this picture, right? There's a very obvious symmetry that goes down this line, both in the detail and the content of the painting. All right, so this symmetry, in my opinion, kind of gives us, it helps us gain this familiarity of a situation that's supposed to be already kind of warm and familial. Okay, so there's this reflection symmetry that's present in this art. Okay, another example of symmetry is a rotational discrete symmetry. So if you take our shape, like we took the square, or you take a hexagon or a star, and you rotate it by a certain angle, you again recover the same shape. Okay? So here's an example of that in art, something by M.C. Escher. We'll see a lot of him today. We see that there's this very cool symmetry present, in that if you rotate these vertices by some discrete angle, you again recover the original piece of art. Okay? We can also think about rotational symmetry that's continuous. So it doesn't matter how much you rotate the shape, or if you want to talk about observing it, from what angle you look at the shape, you'll get the same thing back. So if I were to really draw all of the different rotations you could do, it would just be a completely filled-in circle. Okay, so this is called continuous rotational symmetry. If we were to think about it in 2 dimensions, like just a shape on a piece of paper, that would be a circle. But if we were to put it in 3 dimensions, that would be a sphere. Okay? And we see this kind of symmetry captured in art, such as this painting by Anne Danger. And even though it's a very complex, abstract painting, we still kind of know what's going on. There's still this symmetry that underlies it. Okay, so one more symmetry I'll talk about today is called translational symmetry. And that's the idea that if you look at an object, from no matter where you stand along the object, it still looks the same. So if you were to take a cylinder and just look at one piece and compare it to a piece a couple inches away, it would be the same cylinder. All right, similarly, if you look at a checkerboard, any pattern, any piece of the square that's got just 2 white blocks and 2 black blocks is going to look the same no matter where you are on the checkerboard. So this is what we call translational symmetry. Okay? And we see this show up in a lot of art, such as pop art by Andy Warhol, where we've got all of our Elvises screen printed next to each other. Okay? And I want to show you an even more complicated picture of this, his famous soup can installation. Right? And so this seems like it's a very busy painting. Right? There's a lot of different rows and a lot of different things going on, but it's not overwhelming because we know what it looks like at every point in space. It's a can of soup. Right? So there's this symmetry that really simplifies something that could otherwise be a quite complex piece of art. Okay? So what I want to say to you is then that this symmetry enhances the beauty of art because it gives us a sense of familiarity, in that we can understand the whole painting just from understanding a part of it. Okay, so here's another example from M.C. Escher, where we see that there's just a very simple drawing of a fish. Okay? And so this in itself is not a complicated thing. But when we put it together into a whole painting, we can get this very interesting looking piece of art that's built out of these very simple things just being nested together. All right, but it's not overwhelming because we know exactly what each piece is. It's our fish. Right, so this sense of familiarity is what enhances the beauty of something that might otherwise seem overwhelming or overly complex. So now let's go into physics. Everyone's favorite topic, right? So I'm going to share a little secret with you guys. Sometimes physicists don't want to do math either. I know everyone always says, oh God, why do you like math so much? And we don't all the time, to be honest. Sometimes our calculations can get really hairy, and instead of going through the whole song and dance of trying to calculate something, sometimes it's worth it just to kind of guess if our answer should be right anyways. All right? So that's where symmetry comes in. Why would we do a calculation of something that could be very difficult and potentially wrong if we can just think of the symmetry of the underlying physics and see if that answer is even viable? Okay? So the idea is, going back to our definition of what symmetry is that there's an operation that leaves our shape invariant. Okay? So if a physical system or setup respects a symmetry, if there is this symmetry operation, anything that happens because of this setup must respect that symmetry as well, right? If you can apply the symmetry in the beginning and then physics happens, that symmetry should also be there in the end. Physics doesn't violate this. Okay? So really the question is, why should two identical objects, if they're related by that symmetry, behave any differently? And so let's go through a couple examples of that. So we're going to use symmetry to derive Newton's law. All right, so let's consider that we just have a ball that's moving straight in empty space. Nothing too exciting. There are no forces, nothing acting on it, just a ball rolling. Okay? And then a lot of what we do in physics is trying to figure out what happens next. What's going to happen to the ball? Okay? So what do we need to know about our system to make an accurate prediction? Well, here we can just talk about some of the main symmetries underlying this phenomenon. One, we know that the laws of physics are the same everywhere. It would really be bizarre if me standing over here had one set of rules and me standing over here had a completely different set of rules. And it's not impossible, but it would be really difficult to model a universe that looked like that. Okay? So luckily, we're in a universe where we have this translational symmetry in our physics. Okay? Another thing, if we just look at our ball rolling in front of us, we can look at it right side up, we can look at it upside down, we can look at it from the side. We have this rotational symmetry, where if we rotate the ball along its axis of movement, it's still the same picture. Okay, so with these two symmetries, we can get a lot of mileage out of understanding what's going to happen. All right, so as a scientist, often what you want to do is make a hypothesis and then see what could have happened if this hypothesis were true. Okay, so let's guess that maybe the ball will just start veering to the right for no reason. All right, and in physics, we always need some friends or observers to actually look at what happens and tell us what they're observing. That's what we take as the actual phenomenon, the observation. Okay, so let's have our two friends looking at this ball rolling from opposite sides. So our first observer is standing up here, and they tell us that, okay, the ball veering off to the right, this is what it looks like. Great. Okay? But if we ask our friend who's standing on the opposite side, they'll say that the ball is going off to the left, right? This is just the mirror reflection of looking down on a ball going to the right or looking up at a ball going to the left. So it's the same picture, just looking at it from this different sides of the rotation, okay? So if this person says left, and our first observer said right, how can we predict opposite answers for the same phenomenon? Right? It's this reflection symmetry, that's a good symmetry of our problem, that tells us that these things should actually be the same. Our observations cannot be contradictory. Okay, so there's only really one answer that could possibly be correct then, and that's that the ball just keeps going how it goes. All right, so we've derived Newton's first law just by looking at what symmetries this very simple picture has. Cool. All right, so let's do it again. Now let's do something a little bit more complicated. Let's think about gravity. All right, so consider a star in outer space, or our sun, if you prefer a specific star. Now we want to ask, which way does gravity pull? All right, again, let's think about the symmetries of our problem. If we have the sun, it's basically a big rock in space. It's a sphere. Yeah, okay. So no matter how we look at our sun, it should look the same, because it's spherical, right? If you rotate the sphere, it doesn't change. Every angle will look the same. All right, so we need the direction of gravity, because gravity is produced by the sun, to then match that symmetry of the sun. All right, so one thing it can't do is it can't form loops, right? You may think that, okay, if you rotate it this way, the loop doesn't change. But if I'm standing and looking at the sun from one direction, and then I turn around and look the other direction, it'll appear that the loops flip direction. And what would tell us that the loop should turn right or should turn left, right? There's no rule for that. So that can't be an answer, right? We can't have looking at the sun in a different way change physics. So that can't be right. What gravity also doesn't do is pick a favorite direction, right? Because if I say something is down, and then I have a friend on Mars who's looking at it and says, no, that's actually left, how can we possibly agree, right? How can we say that the coordinates that we define, looking at the sun from some arbitrary point in space, could be the direction that the sun's gravity is going in? Right, so picking this direction, that will not have that continuous rotational symmetry that I've talked about. So that can't be right either. Right, so the only possible answer, there you go, is that we either have gravity, oh man, punchline, all right, is that the gravity points in or out, right? And anyone who's huddled into their phone too loosely knows which direction things fall. Okay, so just a little bit of experimental data, sorry your iPhone, and by knowing the symmetries of the sun, we were able to deduce which direction gravity should point. All right, so I have one more for you, and you're going to help me out. Let's think about electricity. So the physics behind electricity is you have a wire, and there's a bunch of electrons marching along this wire. Okay? Electrons carry an electric field, and that's some electric energy that's stored around the electron, and it has a direction, just like gravity is a field that has a direction as well. Okay? So what does the electric field of the wire look like, of this whole configuration of the electrons going through, let's consider this to be infinitely long piece of wire, right? When you're an electron, even a couple inches seems like infinity. So that's a good, okay approximation. All right, so first let's start off, and I'm going to ask you guys, what symmetry does a wire have? If we extend this off infinitely in either directions, what symmetry does this have?
Translation.
Translational, nice. Cool. So even though the electrons themselves are moving, the density of electron is pretty close to constant, right? So just like if you have a river and the water's going through it, it's not the same molecules of water at every point, but it's the same current, right? So we have translational symmetry in our wire. Okay, now let's think about the electrons. What kind of symmetry do these guys have? We call them point particles. What does that inspire? I hear some whisperings.
Rotation.
Rotational, great. Yeah. So they also have this rotational symmetry. We can treat them like little spheres. Okay, and in fact, we can use the same intuition as our electric field as we did for gravity. So we see that what's going to happen is there's going to be a field that's pointing either inwards or outwards from the charge. So the direction is just defined such that the physics makes sense. So if you have a negative charge and a positive charge, you want them to attract each other, right? So you just define the fields to make sure that that is actually what would come out of your predictions. Right? And we would have had the same problem in gravity as well. But there's only one charge in gravity. Right? In electromagnetism, we have plus and minus, positive and negative. But in gravity, we only have plus. We only have mass. And mass will always bring each other together. Right? So the field lines here are defined by convention. The field lines in gravity are defined by the fact that mass can only bring each other together and not repel. Great. So we have our field configuration of our electron. We know the symmetry of the wire. Let's put it together. Okay? So when we combine these two things, we see that the field will basically look like it's pointing radially inward all along the wire. Okay? So that's a pretty interesting result. And we didn't need any sort of math to do it. Speaking of electricity. So when people ask me, why do I like physics? They always seem like that's just a terrible thing to like. Like it's just math and no intuition and it doesn't help you really understand anything. But what I gotta say my favorite part about physics is the fact that you can have two very distinct pictures to describe one physical phenomenon, and they agree. Alright, so maybe if you went to undergrad and you studied physics and took a class on electromagnetism, you were taught Maxwell's equations. Which are these guys, right? And so this might look a little hairy, but in fact I think that this is a pretty beautiful thing as well. We got pretty lucky that we live in a universe that can be modeled by math at all. Right? You can think about how many things in your life have nothing to do with math. Like if you knew that relationships could be modeled with equations, I would definitely be buying stock in Tinder, right? So this in itself is definitely a form of beauty. Okay, but the fact that we can also... Okay. Oh. We can also just draw... Come on. We can also just draw pictures. And that's pretty amazing too, right? And the fact that we can look at something and make some argument about the symmetry, and that we can write down a series of equations, and we get the same answer, the same predictions, that's really exciting. Alright, so symmetry is really profound in physics because it tells us that there's really just no other answer that could possibly be right. So I want to bring us back to this point that I made in the beginning about art. Is that the sense of familiarity that we have when looking at these symmetries is that we do get an understanding of the whole just from considering the part. Okay? And we came back to this idea in physics where we have the answer or predictions should be able to reflect the symmetry of the initial setup. Okay, so the parallel from art to physics is that the sense of familiarity that makes us feel this beauty in art is akin to what makes it predictable in physics. Right? These are two sides of the same coin. All right? So I want to ask kind of a deep question as we're wrapping up. Why should we even expect physics to be simple? Okay? So physics is not just a list of facts that describe our universe, it's a model. And we as physicists are trying to better understand our universe by developing this model. Right? And so we use the language of mathematics and sometimes use cube symmetry pictures to try to understand nature, but fundamentally it's just a lens that humans use to try to figure out what's really going on. Right? So if something is very complicated and produces this really interesting calculus problem that's got some weird solution and some weird number of dimensions and all this kind of craziness that we have to manufacture as people, sure, it can look very impressive and will probably make an excellent thesis, but is it right? Does nature really care that this is the solution? So nature, nature is profound. Right? And if we're creating solutions to things that seem very mathematically complicated and weird, it might not be the right answer, right? Humans can create these very clever answers, but nature just is. And so if we're getting these really weird things, chances are we're just not talking about it in the right language. Okay? So the idea is with physics that we want to find the right language to discuss these phenomena such that they do seem simple, because that's the truest way that we can explain them, not the most manufactured mathematical human vision of what's going on. Okay, so I've shown you a couple different symmetries today. We talked about this reflection symmetry, our rotational symmetry, and our translational symmetry, and see how we can both enhance the beauty of art and explain the phenomena of physics. Okay, so these are, again, the same principles of symmetry that help us feel this familiarity in art and give us these predictions in physics. Okay, and this is really just the tip of the iceberg. There's so many other examples in nature that you can consider, right? We can think about table salt and its crystal lattice structure. We can think about humans and how we have this weird bilateral symmetry, or bees that make this hexagonal shape when they form their honeycombs, right? Symmetry is everywhere in nature. And I want to remind you all of this idea that this symmetry isn't accidental. The symmetry happens and there's only one answer that can possibly be when this symmetry exists. Okay, so I encourage you throughout the rest of today to think about where there's symmetry, if there could have been other answers, and if you think that that is what's beautiful about the system you're seeing. Let's just end. Thank you.
Couple of questions while we set up our next speaker.
I know it's morning.
Any other questions?
What kind of symmetry for the honeycomb picture that you showed?
Okay, so that's actually really interesting. So there's this hexagonal symmetry. So each of the honeycomb is a hexagon, and then there's this translational symmetry throughout the entire honeycomb. I looked it up, and the interesting thing is that it minimizes the ratio of honey to wax, because wax is very easy for bees to produce, and honey is much more energy expensive. So this is the shape that optimizes this problem of honeybees don't want to work, but they want something that's like structurally sound in their hive. So that's a really cool example.
Just for